Okay, so here's where we were last time. Well, Monday, so time before last. Last time was the exam, of course. So we had this formula for how to derive the matrix that represents a linear transformation, right? Remember, we have this big idea where we've got abstract things like vectors and linear transformations that take all sorts of weird forms, can be not only inconvenient, but certainly inconsistent in terms of how we represent them. So we pick a basis or a pair of bases depending on the abstraction in question. And the idea is that bases let us represent these abstract things in much more sort of convenient and consistent ways as lists of numbers. Right? Okay, so how do you find the matrix representing a linear transformation? Well, we have this nice formula here. You take the input basis, look at those vectors, plug them into the linear transformation that you're representing, right? And then write the results in coordinates with respect to the choice of output basis. And then whatever you get, those become the columns of the matrix in question. Okay, so we talked about some examples last time, different kinds of examples. So I just want to make an observation now. This is actually pretty closely related to something we saw quite a while ago. Well, last week anyway. Let's consider the special case where you're looking at a linear transformation from a vector space into itself. So W is V. So linear transformation from V to V. And then furthermore, use the same basis for both the input and the output. Right? So we're going to represent input vectors in the language of the script V basis, and likewise the output we're going to represent in the language of the script V basis. Okay. Then what that formula that we just looked at a few pages back turns into is this. And I claim this should look kind of familiar. What this says is the columns of the matrix are the images of the basis vectors. Now, doesn't that sound like one of the first observations we made in at the beginning of this section was when you want to represent a linear transformation from Rn to Rm as a matrix, the columns are the images of the standard basis vectors, right? Well, this is really, really similar to that. In fact, this is a generalization of that first observation that we'd made. Let's just consider what happens if we use if our domain and target here are both Rn, right? If I use the standard basis in Rn as my domain basis, then these become the standard basis vectors EI, right? And then using the standard basis for my target basis, I represent these outputs, these images of the standard basis vectors, I represent with respect to the standard basis. And you get columns are images of the standard basis vectors. Written, of course, in the language of the standard basis. That goes unsaid, sort of the default assumption. Okay. So this fact that we're seeing here, this more sort of general fact, is a generalization of that very first thing that we wrote down last week. Okay. All right. Here's an example of how it can be convenient to represent a linear transformation with respect to a different basis. There is a linear transformation that flips vectors over the line x equals 2y. Now let's just see what that looks like. Here's that line x equals 2y in the xy plane. And if you have, some vector like that, you flip it over that line and you get something like that. And it's not hard to persuade yourself, only geometrically, that this is a linear transformation. If you add two vectors and then flip them, that's the same as flipping them and then adding them, right? Geometrically pretty satisfying. Okay, so how would I write a formula for this? This linear transformation that flips over the line x equals 2y, if you're going to do this with respect to the standard basis, what's not clear, right? I mean, what do you get when you flip E1 over that line? Well, you've got a little geometry problem to figure out what happens to E1. And likewise, what happens to E2 when you flip it over that line? Not immediately obvious. You have a little geometry challenge. Okay, so how to how to write this linear transformation in the language of the standard basis, ooh, gosh, hard problem. So here's the idea. The way we're going to address this linear transformation is let's think about what vectors can we conveniently work with as pertains to this linear transformation. Well, this vector here, 2, 1, has the very nice feature that it's on the line that we're flipping over, right? So how do you reflect this vector v1 over this line? Well, the reflection of v1 is v1. That's easy, right? Now, what's another vector that we can conveniently draw some conclusion about its reflection? Well, if you look at a vector that's perpendicular to that line, such as -1, 2. Good news, right? Being as it's perpendicular to this line we're reflecting over, when you reflect it, it becomes exactly the negative of itself. Again, easy to write down, right? So, good news, while it might be hard to figure out t of E1 and E2, it's really easy to find t of V1 and V2. Okay, now, another observation. These images of V1 and V2, they're very easy to understand as linear combinations of V1 and V2. So, for example, notice this V1 that I have here. I can rewrite that as 1 V1 plus 0 V2. So, I can view T of V1 in terms of this script V basis, this new basis that I've made consisting of V1 and V2. Right? Likewise, it's really easy to write T of V2. This is 0 V1 plus -1 V2. So T of V2, easy to write in terms of V1 and V2. So having done that, this statement here tells me that. This statement here tells me that. And I have now exactly what I need to write this linear transformation T, the reflection over that line. How do I write that in the language of not the standard basis? We decided the standard basis is hard, right? But can I represent this linear transformation now with respect to the script V basis? Well, sure. The images of those V basis vectors in the language of the V basis, those images are those two columns that we computed above, and so easy matrix. Right. So sometimes, this being a pretty good example, don't just assume that the standard basis is the easiest basis to work with, right? Very often there's something comforting about the standard basis. It's we're used to it, But depending on the situation, it may be actually very much in your interest to say, I don't like the standard basis. The standard basis doesn't connect very conveniently to this question. I'm going to choose a basis that I think more naturally connects to what's fundamentally going on with this thing I'm trying to represent. Pick that other basis. It might be a lot easier in the language of that other basis to represent the linear transformation you're interested in. So I think this is a nice example of that. Okay. All right. So this next page of notes is a lot of setup, the purpose of which is to illustrate a point. So I can't make the point until after I've done the setup. So if you'll just bear with me for a moment here, here's the setup that has to get done. Let's suppose we have some linear transformation, T from V to W. Maybe these are RN and RM. Maybe they're not. Whatever. So let's consider now some bases. This domain. Here's a couple of different bases, let's say, for that domain. So one of them I'm going to call S, one of them I'm going to call V. And I'm going to call the vectors in those bases E1 through En and V1 through Vn. Whatever. Okay. Likewise, the target. It's a vector space. There's a bunch of different bases for that vector space. Let's call one of them S2. Let's call the other one W. Again, names for those vectors. This is just arbitrary setup, right? Okay. Now again, certain amount of setup. I want to tell you more about this vector here, V1. I'd like to tell you what that vector V1 is. How am I going to tell you about a vector? Well, the way we describe vectors is by listing their coordinates. Wait a minute, what are coordinates? The coordinates with respect to some basis. So if I want to describe V1, how am I going to meaningfully tell you what V1 is? I've got to tell you its coordinates with respect to some other basis. Let's use the S basis. So how do I write V1, in other words, as a linear combination of the S basis vectors? Well, and again, this is just setup. This is not a derivation. I'm just saying hypothetically, let's pretend that those coordinates are these numbers, C1 through Cn. And likewise, I want to tell you, just to have something down on paper that we can work with, I want to tell you about this vector. I'm going to tell you about that vector in the language of a given basis. I'm going to choose this S2 basis. And those coordinates, how do I write W1 in terms of those E vectors? Let's say those numbers. Okay. I haven't done anything other than just label a bunch of stuff yet. Okay. All right. Now, keep in mind, we've got this linear transformation T. Right? T I can describe as a matrix if I choose some bases. So let's pretend that I want to describe T with respect to these two bases, S1 and S2. So I want to use the S1 basis for the input vectors. I want to use the S2 basis for the output vectors. With those languages picked, I can describe T as a matrix with respect to these bases. And let's say that that matrix is A. Again, I'm just putting labels on things. Likewise, T with respect to these other bases, M. Just putting labels on things. Now keep in mind, these two matrices, they represent the same linear transformation, T. I'm just representing this linear transformation in different languages. Up here, input vectors are in S1 language, output vectors come in S2 language. Down here, same transformation, but input vectors come to you in V language, and output vectors come out in W language. So we're representing the same thing, but in different languages, so we get different representations. Okay. All right. Again, nothing's really happened yet. This is just content. I'm just setting the scene for a statement that I'd like to make. Talk about different ways that we can make the same statement. Here is the statement that I want to make. I'm not saying this is a true fact for all linear transformations, certainly not. But let's just say, hypothetically, that T of V1 is equal to W1. Let's pretend. Okay. With all of this setup having been made, and by the way, not particularly rare, right? Very often we have a domain with which there are different bases that we might want to work with, right? Likewise, the target. There might be different bases that I would want to work with respect to. Suppose T of V1 is equal to W1. Here's the punchline I want you guys to all kind of get comfortable with, and that is that all 5 of these statements say exactly the same thing. And it's weird that these 5 pretty different looking statements are in fact all identical statements. Right? So again, that's the purpose of this example, is to expose you to this weirdness and then try to get you to think in terms of how you can recognize this kind of thing. So the first statement, the third statement is the first one I'll talk about. It is obviously that same statement, right? Perfect. It's identical, exact same statement. And now let me talk about these sort of top 3 at first. We'll get to the bottom 2 in a minute. These top 3 statements are just the original statement followed by an adaptation in terms of how would you say this within a particular language. How would we say T of V1 equals W1 once I've decided that I want to use the S1 basis to represent input vectors, and I want to use the S2 basis to represent output vectors. That's all this is saying. But it's still T of V1 equals W1. It's just that statement understood that I want to say that statement in a certain language. Okay. All right, and now how do I rewrite that? Well, remember we have this setup, and this linear transformation T in the language of the standard bases, I've already given that matrix a name, A, so I can just rewrite it. That's just A. That's what A is. Right? How do I represent V1 with respect to the standard basis? Oh, well, I already gave some names to those coordinates. V1 in the language of the S1 basis, C1 through Cn. And likewise, W1 in the S2 basis, D1 through Dm. Okay, so I hope you can see that these three statements, again, they all say the same thing. This says a statement about abstractions. This says I would like to make that statement about the abstractions with respect to the standard basis. And then this statement up here is just making that statement with respect to the standard basis. All the same. All right, everybody on board? So likewise on the flip side down here, looking at these three, we've got that statement. This says, let me make that statement with respect to a different pair of bases. Let me zoom back in here. So looking at these two, T of V1 equals W1, same statements. It's just that here I've decided I want to represent input vectors in script V language, and I want to represent output vectors in script W language. And finally, rewriting these, actually, numerically as matrices and lists of numbers. I'm going to go back up to here. In V and W language, T is represented by the matrix M. Again, that was just a choice that we made. It was a label we already decided to put on what that matrix would be. We haven't put labels on these things. How would I represent V1 in the script V basis? The only choices that I've made about how to write V1 are how to write V1 in terms of the S basis. I haven't decided for sure how do I want to represent V1 with respect to the V basis. But that actually is something I don't get to choose. That's something that's already dictated by the fact that V1 is one of the script V vectors, right? And so let's write this out explicitly. I'm going to come back down here. Let's see here. I'll zoom in a little bit more. Let's look at how would I write V1 in terms of the script V vectors. Well, it's some linear combination of V1 and, this is going to be easy, right? I get to put whatever I want in there. My goal is to make this equation work, right? So let's put let's say 1 V1 and then plus, 0 V2 plus 0 V3 plus etc. plus 0 Vn. That's how I can write V1, let's see here, this vector V1 as a linear combination of the script V vectors. We'll just use these coordinates, which are a 1 and a bunch of zeros. So again, I don't get to pick that. I don't get to choose. It is unavoidably the case that V1 is this linear combination of the script V vectors. Okay, and then analogously for this right here, how do I write W1 as a linear combination of a list of vectors that includes W1? I don't have a choice, right? There's only one way to do it. W1 is 1 times W1 plus, and then nothing else, of course, because we're already done. Okay. All right, so it's kind of weird to have 5 different ways of representing the same thing. Particularly weird, I think, is when you look at the extremes over here. So that statement and this statement. How should you recognize going forward that these two very different looking equations, in fact, really morally say the same thing? That they're about different matrices being multiplied by different column vectors to get, well, in fact, the different column vectors. They seemingly have nothing in common. So here's the way I want you to approach this, and I think this is a very important thing to do when you are looking at matrices that represent linear transformations. Kind of always be thinking in the following terms. And I'll show you how to go, let's say, this way. The equation that you're starting with. Ask yourself, first of all, what do I know about any of these things? And I already know something about that matrix. We've already decided that M represents this linear transformation T in a certain language. It represents T in, V language for the input vectors, W language for the output vectors. That is what should motivate you to not only think of M as representing T, but also accordingly to think of these coordinates down here as in order for this to make sense, to unavoidably need to be representing vectors with respect to the bases that M is with respect to. Right? So let me come back down here. Let me zoom back in. So if M is representing T using script V, right, for the as the basis for the inputs, then these numbers here have to represent something with respect to the script V basis. Now, this is what it means for a matrix to represent a transformation, a certain choice of basis for the input. That means that that whatever vector you multiply by, that's coordinates with respect to that basis. So then you just have to ask yourself the question, well, then, what is the corresponding, what is it that goes here? What vector is the 1, 0, 0, 0, etc. linear combination of the V vectors? And you just write down that linear combination and it's V1. Okay. Similarly, what does this represent? Well, we already agreed that M is representing T with respect to bases V and W. That means we know that the output vector is coming in W language. That means that these coordinates represent something with respect to W. What vector is it whose W coordinates are these numbers? Well, it's the 1, 0, 0, 0, etc. linear combination of the W vectors. And again, multiply that out and you get W1. So, not hard to see how you can interpret from there to there, right? The equation, what you know about one of the participants in the equation tells you how you should be interpreting the other participants in that equation. And then proceeding along, right, you can just decide, well, let's see, how does, let's see, I've gotten out of my own way here. We're trying to figure out how does that equation relate to that equation. We know M relates to T. How does T relate to A? In what way is A representing the T matrix? Well, with respect to the standard bases. Right? Because A represents T with respect to the standard bases, I know then that over here I need to be converting in the language of these standard bases. And again, those numbers are already settled. Okay, so there's a lot to keep track of, right? But this is kind of the mindset, and I want you guys to be on the lookout for this. It's very useful to be able to look at something like this and then just, in the context, you got to know what's given in the setup that you're considering, but knowing that this is in VW language, interpreting these accordingly, realizing these are representing certain vectors, and then realize that you can represent them in other languages in different ways. So eventually the goal will be to look at these two statements and kind of at a glance realize, those are the same statement. Okay, so spend some time with that. This is, I think, a really good example for cutting your teeth on this particular goal. Okay. All right. Okay. By the way, in case you haven't noticed, the book in this section covers the topics in a different order than I do. I just feel like it makes sense in the order that I'm doing it here in the lecture, and of course in the lecture notes. So heads up, right? So when you compare with the book's presentation, you're going to see some sort of seemingly out of order choices. So you can decide for yourself which one you like better, which one you think makes more sense to you. Okay, so change of basis. Here's a very reasonable thing to want to do. Suppose I have a vector written with respect to some basis. I know the coordinates of this vector with respect to the v basis. And suppose that while that's all well and good, I need to represent that vector with respect to a different basis. So I want to do something to this list of numbers to interpret instead this other list of numbers. Now, very importantly, even though something's happening here, very importantly, notice that the vector itself is not changing. I'm not saying I want to change the vector. What I want to change is the language with respect to which I talk about it. Right? So you might say how do you translate, right, running with the language metaphor, how do you translate a vector from one language to another? So two things you could do. One thing you could do is every time you find yourself with this circumstance, interpret first what is the vector itself, and then ask how would you write that vector with respect to the W basis. This is sort of the brute force way to do it. The clever way to do this is to realize that what we're talking about is actually a linear transformation. Right? What we want to do here, if you think about it, and let's take a moment to do that, we would like to understand this linear transformation, the action of doing absolutely nothing to the vector. And we would like to understand how to not change the vector. I just want to understand this process of not doing anything to the vector, where the input I would like to interpret with respect to the script v basis, and the output of this action of doing absolutely nothing, I would like to understand with respect to the script w basis. Now, this is kind of a smart alecky observation, but in fact, if you do this, interpret the act of doing absolutely nothing with input with respect to v, output with respect to w, you accomplish exactly that goal. Okay, so good news. We know how to represent a linear transformation with a matrix. All right, we have a formula for exactly how to do that. This matrix that converts, as we know, we're set it up there, it converts v coordinates, multiply by this matrix IVW here, and out comes W coordinates. We know the formula. And the formula for such a matrix is this. Right? This is a copy from several pages back. We talked about this on Monday. Take the input basis vectors, do the linear transformation to the input basis vectors, write your results in the language of the W basis. Don't forget, this linear transformation does absolutely nothing. Right? So I, the action of doing absolutely nothing to VI, gives you VI. Okay. So, very handy formula for how to compute this change of basis matrix is just take the input basis vectors and write them as columns in the language of the output basis. Okay. All right, and that will accomplish the change of basis goal that we're interested in. Okay, so let's see an example. So suppose I'm in R2. Notice that we have a standard basis for R2. That's the usual, 1001 standard basis in R2. Suppose we have another basis for R2. V1 and V2. Now, I'd like to tell you about these two vectors, V1 and V2. I mean, if I want to use them as a basis, you need to know what these vectors are. How am I going to tell you about V1 and V2? Well, I'm going to tell you their coordinates, but I've got to tell you their coordinates with respect to what basis. So we're going to use the standard basis as a way of telling you the coordinates of V1 and V2. And so here they are. They are 1, 1, and negative 1, 1. Right, so very often this equation here would just get written as, V1 equals 1, 1. Right, and the only thing is, if I write V1 equals 1, 1, it's not clearly indicated what is the basis with respect to which these are the coordinates, right? So here I'm just being a little bit more explicit. I'm saying, by the way, in case there was any ambiguity, I'm telling you about V1 with respect to the standard basis. Okay. All right. So given this, how would I do a change of basis from V coordinates to S coordinates, right? If I maybe I've got a bunch of vectors that are written in V language, and I would like to know how to represent those vectors in S language. What is the magic matrix that I can just multiply by and do the translation automatically? Okay, well, that's the matrix on the previous page. Right, so the columns here, the columns of this change of basis matrix are, take the input basis vectors, write them in the language of the output basis. That's the formula on the previous page. Notice these two columns were in fact given in the statement of the question. Lucky break. And so there's the matrix that does this. So this thing right here is the change of basis matrix from V to S. So this matrix, and we'll see an example anyway down below in a moment. This matrix will multiply by V coordinates of a vector and will then return to you the S coordinates of exactly the same vector. Okay, let's see this in action. This is what I like to call a sanity check. I just want to, I'm going to use this change of basis matrix that I claim, allegedly will do the change of basis I just described. Let's do it in an instance where we already know what the answer is, and let's make sure it gets the right answer. Okay, so the instance where we already know the right answer, the first in such instance, is the vector V1. So let's see. Well, here, let me zoom. I already know how to write V1 with respect to the script V basis. How do I write V1 as a linear combination of V1 and V2? Easy, right? V1 is one of the vectors, V1, V2. So easy to write those coordinates. By the way, I encourage y'all, think it through, make sure you're comfortable with this observation here. Make sure that you can recognize, given a vector, given a list of basis vectors, especially in the situation where one of them is one of these, make sure you can recognize the coordinates. Okay, so I know that the script V coordinates are 1, 0. This same vector V1, I also already know its S coordinates. That was one of the givens up here. V1 S coordinates are 1, 1. So I already know that the change of basis matrix, whatever this thing is, it had better multiply by these V coordinates to give me these S coordinates. So let's just check and see if it actually did what it's supposed to do. This change of basis matrix, this thing here, does it multiply by 1, 0 to give me 1, 1? Why, yes it does. That's just arithmetic. I'll let you guys multiply that out, think through for yourself. But sanity checked, right? This has done correctly what it's supposed to do in the case of the V1 vector. Likewise, in the case of the V2 vector, here's how you write V2. as a combination of V1 and V2. Again, it's one of the vectors in the list. It's easy to write the coordinates. Make sure that make sure you're comfortable with this. So there's the V coordinates. Here's the S coordinates. Again, they were given, right? So in the case of V2, where I want to do nothing but convert from V coordinates to S coordinates, does this matrix do that? Is this arithmetic correct? Why, yes, it is. And again, that's easy multiplication, and confirm for yourselves. Okay. All right, quick observation. If you want to do a change of basis the other direction, suppose you know this. Suppose you know how to do a change of basis from V to W, but you would like instead to do a change of basis from W back to V. How do you change basis the other direction? Hopefully no surprise here, but the inverse matrix does that. Really easy to see why this is true, and that is that this is an easy equation to write down. Let's walk through this equation, make sure everyone's comfortable with what this equation says. This says that if you give me a list of numbers, right, if you interpret those list of numbers as W coordinates of some vector, if you take those W coordinates, if you convert those W coordinates to V coordinates and then convert those V coordinates back to W coordinates, well, grand total, you've done absolutely nothing, right? So the act of multiplying by these two matrices in succession should accomplish the same thing as not multiplying by anything at all, or said differently, but multiplying by the identity matrix. So these two matrices, therefore, are clearly inverses of each other, and thus that. Everybody on board? Okay. All right. Okay, a little bit of semantics that we have to talk about, and this is uncomfortable. Man, this is annoying. Let's see, where do I want to write this down? So let's look at here. Let's look at this equation. What does, this matrix that we're describing, IVW, note that converts V coordinates to W coordinates, right? So the input basis is the V basis, the output basis is the W basis. This matrix, when you multiply by V coordinates, gives you W coordinates. What will we call this process of converting V coordinates to W coordinates? I have a proposal. We're changing the language that we're using to represent the vector. We're changing from the V basis to the W basis. From V to W. Wouldn't it seem reasonable that we call this a change of basis from V to W? I think it's highly plausible. Yeah? So everybody see why I'd like to call this change of basis from V to W? Okay. If you've read ahead in the book, you may have already noticed this. Maybe not. It's fine. The book calls this matrix the change of basis matrix from W to V. It seems backwards. Doesn't that seem backwards? Does everybody see why that seems so counterintuitive? We are converting from V coordinates to W coordinates. V to W seems really, really unavoidably what this ought to be called. As I've noted here, right, from V to W, vector not changing. Okay. So why does the book make this seemingly backwards choice? Why does the book call this change of basis matrix from W to V? Well, it's not actually the craziest thing in the world. Here's another true fact. This exact same matrix, computed by exactly the same formula. Here's another true fact. And I'm going to justify for you why this is true. But if you were to take this matrix, put it on the right, and multiply not by a vector, in the language of a certain basis, but multiply it by a matrix whose columns are a given basis, right? Multiply it by this matrix here, whose columns are the W vectors. Let's say in standard basis language. If you multiply that out, you get a matrix whose columns are the V vectors. You do. Let me persuade you why this is. What are these coordinates here? This first column. These first column's coordinate says, if I wanted to produce V1 as a linear combination of the W vectors, what should my coordinates be? These are the coefficients in a linear combination of the W vectors that produce V1. So, in this matrix multiplication, when you take those coefficients and you take that linear combination of those W vectors, you get V1. Right? That's the definition of the V1 coordinates. V1's coordinates with respect to the W basis. And then, by the way, likewise, the next column here is V2 with respect to W, and so you get V2. So this is a true fact. This matrix, and this is I sort of assume the book's point of view, why they call this from W to V. It's very confusing. All right, so let me tell you why I want to use the terminology that we're using. We're gonna go inconsistent with the book on this one, and the reason why is in this course we are not going to do that at all. We have no use for this in Math 216. Now it has uses in other areas. It's right. It's very interesting, true fact, useful in a lot of ways. It's just not something we're going to use in Math 216. In Math 216, this is what we're going to be doing a lot of. We're going to be taking matrices and multiplying them by one, coordinates with respect to one language and interpreting as coordinates of the same vector with respect to this other language. So since this is the application that we're going to be using, I feel like we should use the terminology that's consistent with the application we're going to be running with. Okay, so one of the lessons I want to urge you to keep in mind is always be on the lookout outside of the context of Math 216. If someone gives you a change of basis matrix and says, hey, this is the change of basis matrix from V to W, you got to say, hey, well, slow down. What do you mean by that? In which sense? Right, so a great way to arbitrate is ask them, what's the formula for this matrix that you just gave me, right? And then you can interpret appropriately from that. And make sure that you're interpreting it the way that they intend. Okay, now let me comment a little bit about, the convention in Math 216 in this class. All of my exams have been and will continue to be written with this meaning of this phrase, change a basis matrix from V to W. That phrase means this notation, which is computed by that formula. Okay. Which applies in this way. Okay. This is the convention for Math 216. Good news on the homework questions. In the vast majority of the homework questions, the book doesn't write the language at all. The book in the homework questions just writes this. Well, the book and I agree on what that is. Right? The subscript is always the domain basis. The superscript is always the target basis. Again, unfortunately, in different different books, this might be backwards, or it might be, who knows what notations other people might have. So always be on the lookout for that. But in Math 216, subscript domain, superscript target. The book has the correct formula for this matrix whose notation the book and I agree on. That's all consistent. No problems. It's just the language. It's just when they write out the words. This is where the book and I disagree. And in the homework exercises, they almost never make use of this language. They just write the formulas and the notations. So the one exception, question 1 on the homework. they say change of basis matrix, and I think they say from alpha to beta or something like that. So in that situation, they use this construction, but they mean it in this other sense. So when you see that homework question, it's number 1 in section 5.3. When they say change of basis matrix from alpha to beta, they're saying it what I would like to call backwards. Just interpret it the way that they intended. In other words, interpret it like this, right? And then proceed to do the homework problem, the way, again, interpreting it the way that the book wanted you to interpret it, and then we'll write it down like this. Okay. All right. So apologies for the situation. This is a lesser of two evils situation, and I think this is that best choice. Okay. How do we do change of basis for linear transformations? So a similar situation. We talked about change of basis for vectors. We've got this abstract thing of vector, and I've got it written very conveniently with respect to one basis. I would like to now write it very conveniently but with respect to a different basis. How do I change its representation? How do I translate from one language to another language? Same question comes up with linear transformations. Suppose I have a linear transformation here from V to W. Well, maybe I know how to represent that with respect to a pair of bases V and W. So maybe I know this matrix. Right? But rather, I would like to have, how do I represent that same linear transformation, but I would like to represent it with respect to these different bases. I would like to represent it with respect to V prime and W prime. How would I use my knowledge of this matrix in green to help me figure out this matrix in blue? So again, it's just a translation, right? So neat observation here is that, having made that and having made that, notice that I can kind of fill in the rest of this diagram by observing that these two sort of end caps of this little prism-shaped diagram are just change of basis. These are vector change of basis diagrams. Both of these say I have some vector up here. I know how to say it in V prime language. How do I say it in V language? We already understand how to do that. So the nice punchline then is, if you know this and you would like to know this, then very simply, this thing you want to know, step 1, do that, convert from V prime language to V language for the input vector. Then do the matrix that you know how to do. Right? And finally, your result, which of course now notice here this output from T is in W language. Well, let's convert from W to W prime language, and again, change of basis. So this one little formula right here allows you to do that conversion. Everybody see how that works? So you have a choice on how to think about this. I think there's a lot of value, and I encourage you to think about how this diagram represents what we're talking about here. But you can also, just kind of for convenient use, you can note that this equation by itself, independent of the diagram, this equation makes loads of sense. Let me walk you through how this diagram makes sense, independent of forget the diagram, right? This says, look, somebody's going to come to me in V prime language, and they want me to interpret that vector as such, do the linear transformation, and then write my result in W prime language. Okay, you're coming to me in V prime language. First thing I want to do is take that vector input in V prime language. Let me convert that into V language. Because if you come to me in V language, I know how to do the linear transformation in V language. And I will get an output in W language. Oh, wait. They wanted the output not in W language. They wanted the output in W prime language. Having done the T, let me convert at the end, and that gives me what I want. So this is really easy to just kind of talk through independent of the diagram. Y'all have a great weekend. See you later. Hang on just one